Hi, everyone. So good evening. And today we are in the week 12 problem solving session. So, so this is the last week of this course, NMR Spectroscopy for Chemists and Biologists. In the next week, we will have a 1 hour session where I can take up your doubts, or I'll just give a summary of the entire course. This will help you in attempting or if you are sitting for the exam, then that will be beneficial. So I will wait for 2 to 3 minutes and then I will start today's session. I will wait for other learners to join. So I hope you all remember what we were discussing in the last session. We were uh, we were learning in detail about two-dimensional correlation spectroscopy experiments. So in there we had seen what will be the fine structures in the diagonal peak and in the cross peak of a 2D cozy experiment. Then for a three-coupled spin system, which is linearly arranged or which is uh, arranged in a triangular fashion. So in those cases, how many components we will have in the cozy spectra, and how will the fine structures, what will be the line shapes, and the character, what character will they have? So those also we had seen in detail. So we will continue today with the two-dimensional NMR experiments. So today we will mainly talk about HSQC experiments, and also we will see how scaling is done in two-dimensional NMR experiments. Okay. So I hope all of you have gone through the week 12 lectures. I hope you are able to follow what is being taught. And so I will go through these concepts today and clear your doubts and certain and some questions which are there in your assignment as well. We will solve them. Okay, so I will start. I will share today's slides. Yeah. So hello and good evening, everyone. I'm Akash Jyoti Pathak. I'm a PMRF for this course, for this NPTEL course, NMR Spectroscopy for Chemists and Biologists. Uh, and I'm a PhD scholar here in the Department of Biosciences and Bioengineering in IIT Bombay. So yeah, today we are in the week 12 problem solving session of this course. So I will start today's session. Just wait for just give me a second. Okay, so few learners were not able to join, so I shared the passcode and meeting details. So that's why there was a delay. I will start the lecture. Yeah. So I hope the slides are visible. So yeah. So in the last session, we were discussing about the two-dimensional correlation spectroscopy experiments, and we had seen that in a two-dimensional correlation spectroscopy experiment, there are two axes. One is the F1 axis, and another is the F2 axis, and we get two peaks over there. One is the diagonal peak. The diagonal peak is a indicates the it is auto correlation between two nuclei. So it does not give us any information, but they are still present in any two-dimensional NMR experiment. And the cross peaks that we get, those are those are the information carriers, and they give us the information whether one nucleus or one proton is coupled to the other proton through bonds, through chemical bonds. Now, today we will look into how scaling is done in two-dimensional NMR. So, what do we understand by scaling in two-dimensional NMR? So, basically, as we had seen that, So in this 2D cozy experiment, there were two axes. This one was the F1 axis. This one was the F2 axis. Now in the F1 axis had the information of J coupling, and F2 axis had the information of chemical shifts. Right. So now if we yeah, now scaling therefore can be done. Scaling means that uh, if we want to look at the peaks that we get in the F1 and F2 axis in greater detail, then that would mean scaling. So either we can scale up the peaks in the F1 axis, or we can scale it in F2 axis. So there are two parameters can be scaled. One is the coupling constants and or the chemical shifts. And so how do we so scaling? One thing to note over here is that the scaling is possible only in the T1 period, because in the T1 period, it is also known as the indirect dimension. T1 period is also known as the indirect dimension. In the T1 period, the signal is not collected, right? So any manipulation is possible in the T1 period, because the data acquisition does not take place in the T1 period. Now in the so in the T1 period, there is no detection of the signal, so the pulse sequence can be manipulated. So by manipulating the pulse sequences, what we can do is we can scale up, or we can cause scaling of the peaks in the 2D NMR spectra. Right. So manipulation is difficult in the T2 dimension where the receiver is on and the signal is detected. Uh, so I hope you remember the general 2D uh, NMR experiment. So in a general 2D NMR experiment, we have this preparation time, right? Preparation time, then there is a T1 evolution period, then there is a mixing period, right? Mixing time, and then there is the T2 time period. So in the T2 time period, the FID is collected, right? In the T2 time period, the FID is collected or the data is acquired. Okay. So based on this, so whether it is scaling in the F1 dimension or it is in the F2 dimension, uh, is my screen not visible? Are the slides visible? Just a second, I will check. Is it visible now? Uh, okay. Okay. Yeah. So there can be two types of scaling. One is the J upscaled POSI, and the other is the shift scaled POSI. Okay. Okay. So in the upscaled POSI, as the name suggests, that here what we are doing is we are selectively the J coupling constants are upscaled. And so here the J's will appear upscale, and the T1 evolution period is extended by the introduction of a spin echo sequence, tau 180 degree tau. So what we just now said that in for the scaling experiments, for scaling up, what we do is we cause manipulation of the pulse sequences in the T1 T1 time period. In the T1 time period, so here in this J for this J upscaled POSI in the T1 time period, and extra T1 period or the extent of the T1 time period is increased by introducing this spin echo pulse sequence. Okay, so you remember the spin echo pulse sequence? Yeah, so the spin echo pulse sequence is what? It is tau 180 degree tau, right? So this extra pulse sequence, this tau 180 degree tau, this sequence is introduced, and what is tau over here? So the tau is proportional to alpha T1, right? Tau is proportional to alpha T1, where alpha is what? Alpha is any positive number that is greater than 0. So what will happen as you increase the time period T1? So as you increase the time period T1, this alpha T1 will also increase, right? This alpha T1 time period will also increase. So the separation between this 90-degree X pulse and this 180-degree X pulse will also increase, right? And similarly, this 90-degree X pulse, this 90-degree X pulse, and this 90-degree X pulse, the separation between them will also increase. Now, so now we have to look into that. What will happen? So what changes take place on introduction of this extra sequence? So for this, again, we have to calculate the product of operator at different time points, right? So what is the product operator at time point T1, at time point T2, at time point 3 and 4? If we calculate them, then we can understand that how this J coupling constant gets upscaled, right? So uh, So yeah, so what happens? So whenever you will introduce a spin-echo pulse sequence, what will happen? That this sequence, this pulse sequence, what it will do is it will refocus the chemical shifts. It will refocus the chemical shifts. So in this T1 time period only, so what will happen in the T1 time period? So in the T1 time period only, the chemical shift evolution will take place, right? Yeah, the chemical shift evolution, why will it only take place in the T1 time period? Because following this T1 time period, in this tau period, what will happen? In the tau period, the spin echo pulse sequence will cause refocusing of the chemical shift. Right. We will see a chemical shift evolution only in the T1 period, while the J coupling evolution. Okay, the J coupling evolution will J coupling evolution will take place for the entire time duration T1 plus 2 tau. T1 plus 2 tau, or you can also write it as T1 plus 2 into alpha T1. It is T1 into 1 plus 2 alpha. Okay, so the J coupling evolution will take place for the entire time duration, right? For this entire time duration, starting from time point 1 to the time point 4. Uh, so, uh, while this chemical shift evolution will only take place for the T1 time period. Okay. And one more thing to note is that the spin echo sequence will not affect the J coupling constant. Since the spin echo sequence does not affect the J coupling constant, hence the coupling evolution will happen for the total period of T1 plus 2 tau. Okay, now if we calculate the product operator at time point 3. At time point 3, so what is the time point 3? Here you see that before the application of this 90-degree X pulse, what is the value of this product operator, then what do we find? So this is the expression of the row 3. Row 3. So you see here CKT1, IKY, cos pi JKL 1 plus 2 alpha T1. So this expression, you can see that in the T1 dimension, there is an additional term 1 plus 2 alpha, right? So this cos pi JKL, this JKL is multiplied by a factor 1 plus 2 alpha in the T1 dimension. So you see here in these four terms that we are getting here, in all these four terms, there is multiplication of term 1 plus 2 alpha in the T1 dimension. So what they suggest is, so this factor 1 plus 2 alpha, this factor is causing the J coupling to get to become upscaled. Okay. So this 1 plus, yeah, so that is what is written here. The coupling constant is scaled by a factor 1 plus 2 alpha along the F1 dimension. Okay. So what is this CKT1 if I derive this? So row 1 was what? So in the row 1, you are before application of this 90-degree X pulse. So there are two spins, K spin and the uh, L spin, right? So both are oriented in the Z axis. So it is row 1 can be written as IKZ plus ILZ, right? Now, after the application of this 90-degree X pulse, at that at the time period T2, time point T, at the time point 2, the row 2 will be what? So once this 90-degree X pulse is applied, it will cause the magnetization to shift to the transverse axis in the XY plane, right? So the product operator at time period 2 can be written as minus IKY. So this is Z. So this was oriented in the Z axis. This will get oriented in the Y axis, right? Because you have, after you have applied the 90-degree pulse in the X direction, the Z magnetization will shift to the Y axis, and the similarly for the L spin also, the magnetization will shift to the Y axis, right? And so after this after this time period to second time period of the time point 2, after this time point 2, we will have the this one. We will have the T1, and in the following T1 plus 2 tau period, in the T1 plus 2 tau period, what will happen? The chemical evolution will only take place for the T1 period, while the J coupling evolution will take place for in the both T1 and 2 tau period. Okay. Coupling evolution will happen for the entire duration of T1 plus 2 tau. This is clear. Now, so uh, so after this, after I get this expression of row 2, then in the row, if so this will so following chemical evolution, what will I get? So this I can write it in. So the following the chemical evolution, right? Following the following the chemical evolution, you can write this expression. So you will get what? Ky cos omega k E1, right? Minus IKX sin omega k E1. Okay. And so now what is this CK? So for that I'm deriving this one. So what we have done over here is that here the cos omega k T1 has been written as CKT1, right? And the sine omega KT1, right? The sine omega KT1, the sine omega T1 has been to SKT1. Okay. SKT1. Then this Z hub, after this Z Hamiltonian acts on this, we get this expression. Then for the next 2 tau period, right? 2 tau period, the coupling evolution will take place. So following this, the coupling evolution, yeah, the coupling evolution, you will get this expression rho 3 equal to CKT1 IKY, this entire expression. And if you look at this expression carefully, you will see that in the F1 dimension, you have an it is scaled by a factor 1 plus 2 alpha. Okay. So yeah. So based on what we discussed just now, try to solve this question in the following pulse sequence. So you see here in this figure, the pulse sequence is given. It is 90-degree X pulse, right? 90-degree X pulse following which there is a T1 time period, then tau 180-degree X, tau 90-degree X, and T2 period. So this is the pulse sequence that we were discussing just now for the J upscale cozy experiment, right? So for this pulse sequence, what will be the correct option among these four options? So the first option is chemical shifts appear scaled up in the indirect dimension. So in the indirect dimension means what? In the indirect dimension means in the F1 dimension. In the F1 dimension or along the F1 axis. The J values appear scaled up in the indirect dimension. The J values appear scaled down in the indirect dimension. Both J values and chemical shifts are scaled up in the indirect dimension. So what will be the answer for this question? So just now we saw that in the product operator at time point three, at the time point three, we were seeing that there is an additional factor 1 plus 2 alpha that was multiplied by this JKL term. That was multiplied by this JKL term in the T1 dimension, right? So this causes the peaks that we see to separate. They will get separated by this 1 plus 2 alpha distance. So that is why the correct answer for this question will be what? That the J values appear scaled up in the indirect dimension, right? In the F1 dimension. So based on this expression, if you see here that what was the product operator expression? So it was 1 plus 2 alpha T1. So this means that that in the T1 dimension or in the indirect dimension, or you can also say that in the F1 dimension, all these are same thing. So in all these things, they are getting scaled up by a factor 1 plus 2 alpha. Okay. So the first option is correct. The second option, what does it say? The J values appear scaled up in the indirect dimension. No, the J values. No. Option A is not correct. J values. The J values appear scaled up in the indirect dimension, right? Uh, because because you see here that the JKL term is multiplied by 1 plus 2 alpha. So option number B is correct. The chemical shift appears scaled up in the indirect. No, this is false. The chemical shift will not appear scaled up. Because the chemical shift will only evolve for the T1 period. It will not evolve for this 2 tau period. So only the J value will appear scaled up in the indirect dimension. So yeah, option B is correct. Okay, so now in this case, when we were when this the product operator at different time points were derived, the contribution of the T2 relaxation has not been taken into consideration. Okay, but it is necessary to take the T2 relaxation. We must consider this T2 relaxation because we have introduced this spin echo sequence, right? So in the spin echo sequence, and also because the T1, because of this introduction of this spin echo sequence, the T1 time period has increased, right? So in the increased time period, T1 time period, the T2 relaxation will also take place. And so, uh, so, so if we take this T2 relaxation into consideration, then this rho 3 product operator expression that we were getting, that will get multiplied by us scaling or relaxation factor. This term that you are seeing here, this is called the relaxation factor. This relaxation factor will be multiplied by this with this rho 3 term. Okay, rho 3 term. And so what is this relaxation factor? It is e to the power minus beta T1 by T2 star. So what is beta over here? Beta is 1 plus 2 alpha T2 star by T2. So if we consider this T2 relaxation, then what does this do? It causes the scaling of the line width. Okay, so the J scaling helps to increase the separation between the plus and minus signal in the COSY spectrum, as this leads to the reduction in the cancellation, and this ultimately leads to the reduction in the cancellation of this intensity. So what it is saying is that, so in a 2D COSY, as we discussed in the last class, that the diagonal peaks have what? They have plus 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 character, or the peak intensities have plus 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 signals, and the cross peaks, they have plus minus minus plus this character, right? So these were what? These were absorptive line shape. These have absorptive line shape, and these had dispersive line shapes in a 2D COSY experiment, right? So what we are trying to do over here is, if we are why we are trying to scale up, we are trying to scale up because if the separation is increased between this plus and minus signals, then then the possibility that these two signal intensities may cancel each other, that possibility gets decreased, right? And that is why this J scaling is done. Okay, so yeah, that is what it is written here, that J scaling helps to increase the separation between the plus and minus signals in the COSY spectrum, as this leads to reduction in the cancellation of intensities. Okay, so because these are plus minus character, the cross peaks, if there is very low resolution, then these peaks may cancel each other, and we may not observe the fine structures in the cross peaks. So that is why this J scaling can be introduced by using the pulse sequence that I showed you just now. So as the cross peaks have plus minus character in a COSY spectrum, right? So in a COSY spectrum, the plus minus character is present where? It is present in the cross peaks, right? Over here, this is the cross peaks. These are the cross peaks. So J upscaling increases the separation and hence increases the sensitivity of the cross peaks. Okay. Okay. So is this point clear? So here, what has this 1 by 2 T2 star? This 1 by T2 star, what does it represent? This 1 by T2 star represents a normal line width. Okay. This represents a normal line width. So, so this is the normal white line width, and it is seen that in this pulse sequence, the line width along the F1 dimension will be scaled by a factor beta. Okay, so 1 by T2 star is the normal line width, and if this is multiplied by this factor beta, then that will cause the scaling of the line width. Now, in the if this T2 star is equal to T2, so if this T2 star is equal to T2, then what will happen? So if this T2 star becomes equal to T2, then this beta will be equal to 1 plus 2 alpha, right? Then in that case, beta will be what? It will become equal to 1 plus 2 alpha, and that is the factor. That is the factor that we were seeing when we were not considering the T2 relaxation. Okay, but in the normal conditions, this T2 start is never equal to T2. This relaxation is never equal to T2, and so it is usually this T2 star is so in this event the T2 the line width this line width will become identical to the J scaling factor 1 plus 2. This will become identical to the so in this case what will happen? In this case, this will become identical to the J coupling factor. Right. So the J coupling factor was what? It was 1 plus 2 alpha. 1 plus 2 alpha. So if this T2 star becomes equal to T2, then this one beta will become equal to 1 plus 2 alpha, and this will result in the J coupling, in this, the T2 relaxation factor will become equal to the J coupling factor, right? But however, in most of the time, this condition is not satisfied. So this condition so what I was saying that in the most conditions, this cases, this condition is not satisfied, and thus J coupling helps to improve the resolution within the fine structures. So the resolution within the fine structures if we want to improve the resolution of the fine structure, if we want that these peaks do not cancel each other, we will, if we want to increase the separation between the two peaks, then what we do, then this J scaling factor, it helps to improve the resolution, right? Improve the resolution. So the basically all in all, what is the main information? The main information is that the J scaling along the F1 dimension. Okay, so this one was the F1 dimension, this one was the F2 dimension. So the J scaling along the F1 dimension helps to increase the separation between the positive and negative signals. So, right. So see this example. So let's see this example. So this is this slide I've taken directly from the lecture slides. So this an example was given in the lecture of a uracil molecule. So in this uracil molecule, here we are seeing the coupling between this H5 proton and this H6 proton, right? So if you see so this is a 2D cozy spectra of uracil, and so these are the cross peaks, right? These are the cross peaks. So these are the cross peaks and these are the diagonal peaks. And for this molecule, this J scale 2D cozy has been done. So you see, observe over here. So this has been blown up or this has been magnified. And what you see over here is that this on upscaling of the J coupling constant, you see that in the F2 dimension. In the F2 dimension, the separation is the separation between these two peaks is 7.6 hertz. It has not changed. Okay, but while in the F1 dimension, this has become 30.4 hertz. So this indicates that there has been a scaling by a factor of 4, right? So from 7.6, it has increased to 30.4. So almost a 4 times increase in the scaling of the uh, scaling from the compared to the compared to the F2 dimension. So compared to the F2 dimension, the F1 dimension is scaled by a factor of 4. So in this case, this 1 plus 2 alpha, this factor is actually 4. Okay. So that is why. So once there, so you see here that these two peaks, you see a peak over here. and there is another peak. So between these two peaks, the separation between these two peaks has increased, right? So because of this, the cancellation of the signal intensities has been reduced because of the increase of the separation. So that is what is the benefit of J scaling. So the J scaling along the F1 dimension increases the separation between the positive. So here you see it has increased the separation between the positive and negative signals in the cozy spectrum, and this has led to reduction in the cancellation of the intensities. As a result, there is reduction in cancellation of intensities. In other words, what it does is it increases the sensitivity in the cross peaks. So the diagonal peaks, there is no change in the diagonal peaks, while in the cross peaks and in the diagonal peaks, no requirement of there is no requirement of this J scaling because the peaks are plus 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 character, right? But in the cross peak, there is a chance that this plus and minus signal intensities may cancel each other. So here on J scaling provides this benefit that it increases the separation and reduces the chances of signal cancellation of signal intensities. Okay, now to try to answer these questions in the above per sequence. So this is again the J scale. This is again what? This is J scale cozy. This is J scale cozy per sequence. This is again a J scale cozy per sequence. So J scale cozy per sequence, it will have what? It will have 90° X T1, then there, then 2 tau time period, and that tau time period is what? It is alpha T1. So in the in this pulse sequence, what will be the correct option? The line bits are scaled up in the indirect dimension. The line bits are scaled down in the indirect dimension. No change in the line width and mixed phase line shapes are obtained. So when we're discussing about line widths, so here the options are based on line width. So you have to they have considered here. You have to consider the T2 relaxation also. So just now I was discussing about T2 relaxation. So if the T2 relaxation is also taken into consideration, then this J scale factor, which was 1 plus 2 alpha, right? This J scale factor 1 plus 2 alpha that gets multiplied by another relaxation factor, right? And this was the J scale factor. G scale factor, but if we consider the T2 relaxation, then this gets multiplied by this row 3, this gets multiplied by another relaxation factor, e to the power minus something by T2 star minus beta T2 by T2 star, right? Beta T2 by T2 star. So what we just now discussed that if we consider this T2 relaxation also taking place, and if this T2 is not equal to T2 star, T2 is not equal to T2 star, then what will happen? Then the line width will become scaled. It will become scaled up in the indirect dimension, right? It will become scaled up in the indirect dimension. So option is correct. Just now we saw here that here I written this expression. So this entire factor, row 3, this one, this entire expression gets multiplied by this factor e to the power minus T2 by e to the power minus beta T2 by T2 star. E to the power minus beta T1 by T2 star. Okay. And beta was what? It was 1 plus 2 alpha T2 star by T2. So this entire you see here that this is T1. Okay. So this if the T2 relaxation is also taken into consideration, then what will happen? There will be scaling of line width in the T1 dimension because this is multiplied by this factor e to the power minus beta T1 by T2 star. Okay, so there will be scaling in the scaling of line within the T1 dimension. Okay. So the row 3 start or the product operator expression that we get if we consider this T2 relaxation, then then the product operator at time period 3. So this is 3. Row 3 means we are writing the product operator at this time period. This entire at this time period, this will get multiplied by this factor e to the power minus beta T1 by T2 star. So there is scaling up of the line width in the indirect dimension. Okay, option is the correct. Now another, so the we so for scaling, there can be two types of scaling we discussed in the initial slides, that there can be two types of scaling. One is the J scale POSI and another is the shift scale POSI. Okay, so if you're scaling up the J coupling, then it is J scale POSI, and if you are scaling it in the F2 dimension, if you're scaling it in the F2 dimension, then it is shift scale POSI. Now this shift scale POSI can also be, it can be either upscaled or it can be downscaled. Okay. The shift scaled cozy, it can be either upscaled. So upscaling means with what? We are increasing, if we increase the separation, if we increase the separation between the peaks in the F2 dimension, then it is then it is upscaled shift cozy. And if we are decreasing the, if there is decrease in the peaks in the F2 dimension, then it can be downscale. It is called a downscale position. Okay. So in this shift scale position, what it means that here the chemical shifts are scaled. Okay. The pulse sequence. So basically, in this shift scale position, we are not altering the pulse sequence. The pulse sequence is remaining the same. It is same as that. It is same as that what was there in the J scale position. So it has a 90-degree X pulse. Then there is a 180-degree X pulse, and then again there is a 90-degree X pulse. Okay. But what is changed in the shift scale cozy is the duration, this time period. There is manipulation of this manipulation between this excitation signal and the detection signal. Between these two signals, the time period is manipulated. Okay. So in this case, the this entire period between this 90-degree X excitation signal and then this 90-degree X detection signal, between this entire period, the entire period is considered here T1. But in J scale cozy, the T1 period was what? It was only restricted to this portion T1. So T1 was equal to 2 tau. Okay, so T1 in the J scale cozy, in the J scaled cozy, T1 was equal to 2 tau, right? But for a shift scale cozy, the T1 is what? The shift scale cozy is taken for this entire duration. It is this 1 minus alpha T1, 1 minus alpha T1 plus 2 tau. This period, entire period is now, this entire period is now T1. Okay. So now, similarly, the same things will happen over here, right? So once you are giving this 90-degree X pulse, the spin will shift to the transverse axis, right? They will move to the, so if you are applying a 90-degree X pulse, initially they were oriented in the Z direction, they will move to the y axis. They will move to the y axis, and then what will happen? Yeah, so that is what I was saying. The evolution period duration is altered. So T1 is called the evolution period. So here we see that the evolution period is altered compared to the J scale cozy, and similar to that. Here also the same thing will happen, that this here also we have this spin echo sequence, right? Tau 180 degree tau 180 degree tau. So before this spin echo sequence, the chemical evolution will chemical shift evolution will take place only till this point. Till this point, before the tau period, before the 2 tau period, the chemical shift evolution will take place. Then the spin echo sequence, what will it do? It will refocus the chemical shifts. It will refocus this chemical shift, and so that is why, because this Pinnacle sequence refocuses the chemical shift, the chemical evolution will take place only before the 2 tau period, while the J coupling will evolve for the entire duration. Okay, for the entire duration. Now, so as we had derived that the product operator expression at different time points for the J scale POSI, if we derive the product operator expression at different time points for the shift scale POSI, then finally at this row 3 or at this time, at this time period 3, time point 3, at this time point 3, the row 3 that we will obtain will be what? It will be cos omega k 1 minus alpha T1 IKY cos pi JKL T1 minus 2 IKX ILZ sin pi JKL T1. So this is this entire expression you will get. Now, if you break this expression and look at each of these carefully, then what you can see that here in now in this case, this this JKL term is not multiplied by any factor, right? That so here what will happen then? Here, since this JKL, in the J scale POSI, this JKL term was multiplied by 1 plus 2 alpha. But here, what we see that this JKL term is not multiplied by any factor, and hence there will be no scaling in the T1 axis or in the T1 dimension or in the F1 dimension or in the indirect dimension. There is no scaling. Okay, but in the F2 dimension, you see in the F2 dimension, this is multiplied by this factor 1 minus alpha, right? 1 minus alpha, and here also you see this is multiplied by 1 minus alpha, while there is no while this JKL term is not remains unaltered. Okay, so that is why the chemical shifts are scaled down by a factor 1 minus alpha along the F1 dimension. So this is multiplied by T1. So this chemical and the factor is 1 minus alpha. So that is why it would mean that there is a downscaling, right? There is a downscaling, or the chemical issues are scaled down by this factor 1 minus alpha along the F1 dimension. Now, then what is the advantage over here? So if it is scaling down the if it is causing a scaling down of the two peaks, then so that will, if there is a scaling down, then obviously what will happen? The separation between the peaks will decrease, right? Your separation between the peaks will decrease. However, the T1 max will go up and the inherent resolution in the spectra will increase. So the T1 max this time, so the acquisition period also has a role in the resolution in the F1 dimension. So scaling down this factor results in an increase in the T1 max, and as a result, what happens is the the resolution in the spectra increases. Okay, is this point clear? So similarly, if we consider, so here in this row 3 expression, the T2 the T2 relaxation was not considered. But if we consider the T2 relaxation, okay, if we consider the T2 relaxation, then this again will be multiplied by this factor minus T1 by T2 star 1 minus alpha plus alpha T2 star by T2. So this multiplication by this relaxation factor causes the scaling of the line width. Okay, so here also you see that this is multiplied by this 1 minus alpha factor, and therefore the line widths are also scaled down, and hence it results in better resolution in the fine spectra in the fine structure. Okay, so So the rho 3, if we consider this T2 relaxation, then this rho 3 can be written in this form. Okay. So now here also, if this factor, if this T2 star becomes equal to T2, then what will happen? If this T2 star becomes equal to T2, I will just include another slide. So what is the expression that we were getting? If we include this T2 relaxation time, then this rho 3 star will be equal to rho 3 into what? E to the power minus T1. Is it being recorded? Right over here. So this rho 3 star will be equal so the expression that we got, if we consider this T2 relaxation, then it will be equal to rho 3 star equal to rho 3 into e to the power minus T1 by T2. That is what we have got, 1 minus alpha plus alpha T2 star by T2 plus alpha T2 star by T2. Alpha T2 star by T2. But if T2 star becomes equal to T2, then what will happen? Then what we will get? Rho 3 will be equal to what? Rho 3 star will be equal to rho 3 e to the power minus T1 by T2, 1 minus alpha plus alpha, right? And hence, what will happen then? So, so if this happens, then there will be no scaling of the line widths, right? Then there will be no scaling of line widths. But if this T2 becomes less than T2 star, or if this T2 star becomes less than T2, then what will happen? If T2 star becomes less than T2, then there will be, then the line width will be scaled down. Will be scaled down, and we will observe. What we will observe? We will observe better resolution in the multiplet structure. So in the multiplet structure means in the cross peak, we were the multiplets that we were obtaining. So they will have a better resolution. Okay. So now I try to answer this question in the given pulse sequence. So you have this pulse sequence shown over here: 90-degree X pulse, 180-degree X pulse, and 90-degree X pulse. And this is the pulse sequence of what? This is the pulse sequence of a shift scale COSY. right? This is the pulse sequence of a shift scale cozy. So for a shift scale cozy, there are four statements that are given in the option. Option A is chemical shifts are scaled up in the indirect dimensions. Chemical shifts appear scaled down in the indirect dimension. J values appear scaled up in the indirect dimension. And option D is J values appear scaled down in the indirect dimension. So what will be the correct option for this shift scale cozy pulse sequence? Just now we saw that this rho 3 star expression that we were getting, if we consider this T2 relaxation, then that gets multiplied by this e to the power. Uh, there is one factor 1 minus alpha, then this T2 by T2 by T2 star, right? T2 by T2 star. And also you have this one, this T1, this 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 T1 term here. Okay, T1 term here. So what does this mean? That just now we saw that this causes what? As we saw in the expression, that this will cause the chemical shift to be scaled down in the indirect dimension, right? Chemical shift will be scaled down in the indirect dimension means when the indirect dimension means what? In the F1 dimension, in the T1 dimension, in the T1 time period. Okay. So yeah, option B is the correct option, right? Option B is the correct option. So did you understand how the scaling down helps to improve the resolution? How does this downscaling helps to improve the resolution of the fine structures in the multiplet? Basically, what happens is this T1 max, this gets increased. So once this T1 max increases, the value of this T1 max increases for a given number of T1 increments, then what will happen? It will cause the chemical shifts to scale down. Okay, this chemical shifts will be scaled down. So what does this mean? That the chemical shift will get scaled down. So if you have, for example, you have 5,000, you have 5,000, the chemical shift range is 5,000 hertz. Okay, the chemical shift range is 5,000 hertz, and if it is scaled down by a factor of half, right? Then in this period, then what we will get? Then this will become what? It will become 2,500 hertz. So in this case, the increment, right? The increment from experiment to experiment, or in this T1 period, will be twice that in the normal cozy, where you had 5,000 hertz. So the increments that you will see on scaling down this chemical shift spectral range from 5,000 hertz to 25,000 or 2,500 hertz will be it will become twice in the normal cozy, and hence the for the same number of increments. For the same number of increments, the T1 max will go up. Right. The T1 max will go up, and therefore the inherent resolution in the spectrum will increase, because this resolution depends on what? It depends on the acquisition time. Right. It depends on acquisition time. It depends on acquisition time. So scaling down of this chemical shift causes increase in the T1 max values, or it results in increasing the acquisition time, and hence the resolution will improve. Resolution will increase. But however, the separation between the peaks will get decreased. That is why it is also called a scale down shift cozy. Scale down shift cozy. Now, there in the lecture there was another concept discussed, which was how to upscale or how to increase the separation. So what we saw just now, that in this shift scale posi, this is what this first sequence, this 1 minus alpha T1 period, this sequence is causing the separation between the two peaks to get decreased in the F1 dimension, right? Or the chemical shift, the chemical shift evolution is getting decreased, but and that is resulting in the separation between the two peaks to get decreased. But there is there is another in the lecture there was another pulse sequence discussed, which showed that what changes can be done here that will cause the upscaling, or that will cause the separation between the two peaks in the F1 dimension to increase. Okay. So I have not discussed that. Directly, let's discuss this total correlation spectroscopy experiment. Okay. So we had seen what is a cozy experiment, right? So in a cozy experiment, the information that we obtain from the cozy experiment is that whether two protons are coupled to each other by through J coupling, which means that if there are two protons, say, give me a second. If there are two protons, say consider this example, CH3, CH2, CH2OH. So this is a propan one all or propanol. This is propanol, right? So from the cozy experiment, what we can the information we will get. So here there are three protons, right? So if we label them as A, B, C, then the cozy experiment gives us the information that this A is directly coupled. This A proton is directly coupled to B proton, and the B proton is directly coupled to C proton. But it will not give us any information whether this A is also coupled to C indirectly or not. Right? That information we will not get. We can uh, so uh, so that is the disadvantage of so that is the disadvantage of that information can never be obtained through a cozy experiment. Okay, because the cross peaks that we get, the cross peaks give us the information whether the two spins are directly coupled through chemical bond or not. But the TOXI experiment, this total correlation spectroscopy, it will not only give us the information that these two spins, that this A proton is directly coupled to B proton, but it will also give us this information. That is, we will also get a cross peak that will indicate that this A spin is coupled to C spin via the B spin. Okay. So it is not directly coupled, but indirectly the A spin is coupled to C spin, or if there were other methyl protons, or so subsequently to how to the so the total, it will give a spin system that is called a spin system. So one proton, so a proton in a molecule is coupled to which all protons in the same molecule. So what are the other protons? Whether it be directly coupled or indirectly coupled. So all the information will be given by a Toxi experiment. Okay. So here, so let's understand this in more detail. So in a cozy, we get cross peaks for only those protons which are directly J coupled to each other. Okay, so that is what I was explaining. So if we will get only a cross peak for this A and B cross peak we will get, right? If because A is directly coupled to B, but we will not get a cross peak for A and C, right? Because A is not directly coupled to C, it is via this intermediate proton. So that is the limitation of this COSI, that it does not give us it only gives us the information of those protons which are directly coupled to each other. But we would also want to know which protons are indirectly coupled to each other. So if we want to know that which protons are indirectly coupled to each other, then we perform this 2D total correlation spectroscopy experiment. So this 2D toxi experiment, this is the pulse sequence of a 2D toxi experiment. So it has a 90-degree X pulse followed by a T1 time period, the small T1 time period, evolution time period, and then a spin lock. This is a spin lock period. This is also called isotropic mixing period. This is also called the isotropic mixing period. And then there is the detection period T2. Then there is the detection period T2. Okay, so this in this spin lock system, this spin lock that is a period that is introduced over here. It consists of many pulse sequences. So those pulse sequences, they are quite complex and they have not been covered in the lecture. Okay, so just uh, we will not go into those details. So whatever has been taught in the lectures, we will try to understand that. So for this 90-degree X pulse is given, and this will cause what? It will cause the spin to shift to the transverse plane, right? So the Z, if it was oriented in the Z direction, and on application of the 90-degree pulse in the X direction, RF pulse in the X direction, what will it cause? It will cause the spin to shift to the transverse plane, to the XY plane. And then it will start evolving in chemical shift, followed by so in this time period. Once it moves to the So once this the spin is transferred in the transverse plane, then it will there will be chemical evolution for the T1 period, and then this will be followed by application of pulses that will resulting in the spin lock. So in the spin lock, there are many pulse sequences which result in the spin lock system. Okay, so in this spin lock in the spin lock period, what is done is a weak radio frequency irradiation is applied continuously for 60 to 80 milliseconds. So in the spin lock period, uh, this a weak RF irradiation is applied for a very long time. While in these pulse sequences, in this 90-degree pulse sequences, we were applying a high or the RF irradiation was applied for a very short time in microseconds. While in this spin lock period, it is applied for a long time in the range of 60 to 80 milliseconds. So this RF irradiation, this weak RF irradiation, how does it help? It causes the proton in one molecule to get coupled to all other protons in the same molecule. Okay, so during this spin lock period, this is the main period. So in this period, the proton in this proton, if we consider this A proton will get coupled to all other protons in this molecule. Okay. So in Toxi, the coupling also take place between faraway hydrogen during the spin lock. So that is the advantage of Toxi. We can also get the information that what all protons is coupled to the proton that we are considering. Okay, indirectly. Okay, that also information we will get. So that is the function of the spin lock period. So what does the spin lock period do? It helps the so what is the spin lock period? First, that it is a weak RF irradiation and it is applied for a very long period of 60 to 80 milliseconds. And in this spin lock period, what will happen? This proton will get coupled to all the protons in this molecule. It will get coupled to all of the protons in this molecule, and as a result, we will also find peaks. We will also get peaks for protons that are far away from the proton that we are considering. Okay. So yeah, so during the spin lock period, the chemical shift evolution is eliminated and only coupling evolution takes place. So in the spin lock period, this chemical shift evolution that is eliminated and only the coupling evolution will take place. And in Toxi, the spins go into a strongly coupled situation, unlike a 2D cozy experiment. So the function of the spin lock period is also this spin lock period. This spin lock period, it has many functions. First, it will cause the proton to get coupled to all other protons in the molecule, and also it causes it results in a strongly coupled situation. Okay, so what is the function of this strongly coupled situation? So till now, what we were considering in a cozy experiment, in a 2D cozy experiment, only the weakly coupled spin systems were considered. So for a weakly coupled spin system, what is that? So in a weakly coupled spin system, omega A minus omega X is much, or it is equal to J. Right. It is equal to the coupling constant. This is for weakly coupled. While if this the separation in this chemical shift is much less than J, then this is a weakly coupled spin. This is a strongly coupled spin system. Okay. So they go into a strongly coupled situation, unlike a 2D cozy experiment. And in the in phase components are so yeah. So this is the density operator expression. And here you see that there are two terms. One is this diagonal peak. This is the term that will be responsible for the diagonal peak, and this term will be responsible for the cross peak. And so if you now this is what has been written over here is that we have considered the Hamiltonian evolution, or the J coupling evolution. The J coupling evolution E is the total the evolution that has been considered. Okay, so for the two spins, for the key spin and the S spin separately, the density operator is written over here. And now if we add this first equation with the second equation, then on addition, what we see is that these terms will get cancelled. Okay, these terms. So here you see that here it is plus 2 IKY ILZ minus 2 ILY IKZ. And in the second expression, the term is 2 ILY IKZ. So this is positive, and this on if you add these two expressions, then these terms will get cancelled. And similarly, this term also minus 2 IKY ILZ, this will cancel with this term. Okay, and so this will become zero. Similarly, here also, and the diagonal peak. So in the if you add these two, then here the 1 plus cos pi 2 JT by 2, right? It is IKX. This is IKX. And here this IKX is multiplied by this factor, 1 minus cos 2 pi JT by 2. So these factors will get, this also will get cancelled. And what we will be left with is this, with this IKX plus ILX. Right. So this indicates that this X magnetization remains conserved during the mixing period. There is in phase transfer that is taking place, and which helps to retain the phase of the magnetization. So this is called isotropic mixing. That is, so here is the expression. So what is happening in the spin lock period? That is the spin lock period. The different time periods after the spin lock period, we will obtain these two, this IKX and ILX. And we see that after this spin lock period, there is magnetization in the X magnetization remains conserved, right? That is why the spin lock period is also called as the isotropic mixing. And the Hamiltonian is called isotropic Hamiltonian. Okay. So, so in this isotropic mixing, there is relay of magnetization taking place. Relay of magnetization taking place means what? This. So what I said that the the proton will get coupled. One proton will get coupled to all other protons in the molecule. Right. So that is what is that is what is called the relay of magnetization. So if it is for this molecule, this H3CH2, CH2OH. So the magnetization from this proton will get transferred to this proton, and then this proton will transfer the magnetization to this proton. So this total correlation spectroscopy is also known as a relayed COSY, because it is similar to what happens in a relay race. So that is why we will not only observe peaks for A and B, but a peak for A and C will also be obtained. So if you take a toxi spectra of this molecule, and say you have these label this as AMX. Okay, so if you so on one axis you will have AMX, in the F2 axis, and in the F1 axis also you will have AMX. Okay, so first you will obtain the diagonal peaks. So A will, yeah, every spin is coupled to itself. So A is M. So you will obtain the diagonal peak and then the cross peak. So so what cross peaks will you observe if you take a toxi? If you take a toxi spectra, then the one cross peak will be obtained over here, right? Because A is coupled to M, and you will also obtain a cross peak over here also because of this relay of magnetization. Because of relay of magnetization, you will also observe a cross peak between this A and X. Okay. Similarly, here for A and M is coupled, but X is also coupled to A intermediate via this intermediate proton, and so you will also obtain a peak over here. Okay. So X and A, so over here. And X and M is also coupled. So that it becomes similar to the triangular AMX spin system that we had seen in the last session. So do you understand this? So this toxi basically the main summary of this experiment of this toxic experiment is that it is not only giving us the information that a particular proton is directly coupled to another proton, but also we are getting the information that what other protons it is coupled indirectly, right? That information also we will get. But one thing to note over here is that, for example, if there is a ketone between these two methyl protons, then yeah, so if this proton is replaced by a ketone, then you will not observe a cross peak between this A and X. So, for example, you have this if you have this CH2. Add one slide. The one thing you must understand over here is that, for example, you have a molecule like this, CH3CO, CH2, CH2, CH3. Okay. Now, in this case, so for this molecule, if you record the toxi, then so if we label these protons A, B, C, D, then in the toxic spectra, what we will find that this A is coupled to B, we will get a cross peak for A and B, and you will also get a cross peak for A and C, but you will not get any cross peak between A and D because here this CH2 group is replaced by this ketone, and this prevents the coupling from getting transferred to this CH3. So you will get a separate peak for this one. You will not get a cross peak between A and D. So that is so the information that we get from COSY is that what are the protons that are present in a spin system. So all these A, B, and C is part of the same spin system. A, B, C are part of the same spin system. So that information, whether the protons are part of the same spin system or different spin system, that information is obtained from a toxic experiment. The same spin system, and this D is part of different spin system. So that is the main crux of this experiment. Okay. If we leave aside this density operator expression and the mathematical calculation, then the advantage of using the proxy is what I discussed just now. Okay, so the advantage of proxy is that it gives interaction between all the hydrogens which are coupled to each other, either directly or indirectly. Okay. So the toxic correlates the chemical shifts of all homonuclear spins that are coupled together through J coupling. So Yeah, all homonuclear space is proton-proton coupling that we are seeing over here, right? So that is why it is the chemical shift of all homonuclear spins to J coupling that we are getting. Yeah. Just a second. So let's just derive this expression. So in this row one period. So what was the pulse sequence that you had for this? The pulse sequence that you had for this toxi was that you had this 90-degree X pulse, right? 90-degree X pulse, and there was this T1 period, and then following a spin lock period, then you collected the FID, right? You collect the FID. Now, if you do the, so this is one, two. If you do the density operator calculations, then what will you get? Right. So in this row one period, you have the K spin and the L spin oriented in the Z direction. So it is IKXZ plus ILZ. Okay. Now once you apply this 90-degree X pulse, then the density operator at time point 2 will be what? It will be minus. You have applied a X pulse, 90-degree pulse in the X direction. So it will, this K spin will shift to the y-axis, and L spin will also shift to the y-axis. Now in this T1 period, there will be what? There will be chemical evolution. The chemical evolution will take place in this T1 period. So, so ultimately the row four. So here there are a lot of pulse sequences. So ultimately the row four that you will get, that will be what? It will be I equal to I Ky, right? I Ky sine omega k alpha T1 plus I Ly sine omega L alpha T1 cos phi j k L T1 T1 plus delta plus 2 I kv Lx ILX, right? ILX sine omega k alpha T1 plus 2 ILZ. uh, the antiphase ILZ. Then there will be what? IKX IKX sine omega L alpha T1 sine omega or sine pi j k L T1 plus delta. Okay, so you observe these two I K Z I L X and these are the antiphase terms, or so this is L spin antiphase with respect to Z, right? So these terms will, these terms will give you the cross peak and the diagonal peak, right? This one gives you the cross peak, and this one gives you the diagonal peak, and this one gives you the diagonal peak. Right? Now try to answer this question. In the toxic experiment, which of the following statements are true? There is in-phase transfer of coherence. There is relay of magnetization. Transfer efficient. Transfer efficiency is worse than in inept transfer. Spin lock leads to isotropic Hamiltonian. So out of these four options, then which are the correct? Which are options are correct and which are wrong? So just now what we said that for a toxic experiment. So what do you have in a toxic experiment? So in the toxic experiment, there is in-phase transfer of coherence. Yeah, we saw that in a toxic experiment, both the diagonal peak and cross peak, both the diagonal peak and cross peak have in-phase character. They have both all the four peaks have plus 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 character. Okay, so this one. All these have in-phase character. Okay, and there is relay of magnetization. So in the spin lock period, what happens? One proton gets coupled to all other protons. So that is what is known as the relay of magnetization. The option C, transfer efficiency is worse than in inept transfer. Is this correct? So we will look at this. This is actually not correct. We will look into this in more detail. But the fourth option, spin lock leads to isotropic Hamiltonian. Right. So this option is also correct. So option A, B, and D are correct over here. Okay. So that is why the spin lock period is also known as the mixing period. So option C, A, B, D are true. Okay. So now, why this option C is false? Why this transfer efficiency is worse than that in inept transfer? So this is the expression that we had derived, right? So this expression, IKX, HET, AGT, IKX 1 plus cos 2 pi JT by 2. So 1 minus cos 2 pi JT and do this expression. Now, if you if you put so actually here if you see, so that there is complete transfer of magnetization between the cross peaks and diagonal peaks in the time period T1 equal to 1 by 2j. Why is it so? Because if you put this value 1 by 2j and this T expression in the expression of T1, then what will you get? So there this expression 1 plus cos 2 pi j by 2, right? So if you put the value t equal to 1 by 2j equal to 1 by 2j, then what will you get? You will get 1 plus cos 2 pi, this 1 by 2j, and this 2j will get cancelled, and you will have 1 plus cos pi by 2. So what is cos pi? Cos 180 degrees minus 1, right? Cos 180 degrees minus 1. So this entire term, this diagonal peak term gets cancelled and it becomes 0. And here in this cross peak, in the cross peak term, if you put this value, if you put the value t equal to 1 by 2j, t equal to 1 by 2j, then what will you get for this expression? 1 minus cos 2 pi j. In place of j, you have You put the term 1 by 2. In place of t, you put the value 1 by 2j, and then you have j. Okay, so what will you get here? You will get 1 minus cos pi. And 1 minus cos pi by 2, this will give you what? 1 minus minus 1, cos pi is minus 1, so this will give you 1. So at for time t1 equal to 1 by 2j, you see that this diagonal peak term becomes equal to 0, and this cross peak term becomes equal to 1, and ultimately this becomes equal to ILX, right? So this means that there is complete transfer of magnetization from the diagonal peak to the cross peak in 1 by 2j time period. In 1 by 2j time period. While in case of INEP, the time period that is required for complete transfer is 1 by j, right? That is why that is why this means that, so this is 1 by 2j means what? It will take less time, right? This will take less time than this. So this means that the transfer efficiency is better for a toxic experiment as compared to an inept experiment. Because for a toxic experiment, the transfer time is 1 by 2j, and for an inept experiment, it is 1 by j. So did you understand all these points clearly? Before moving to the heteronuclear correlation experiments, let me let me show you this in detail. That if we that for this toxic experiment, we have this 90-degree X pulse. Then following this, there is a T1 time period and then a spin lock period, right? Spin lock period, and then there is this the T2 detection period, right? Or FID that is collected. Now, after this T1 period, what we learned that the chemical evolution gets lost in the spin lock period. It gets eliminated. So that is why what happens is we write this HE. H is also known as effective Hamiltonian. H is called the effective Hamiltonian. The effective Hamiltonian gets reduced to this expression 2 pi j k into IL, or rather 2 pi j I k into I L. Okay, and this you can further write it in this form 2 pi j I k into I L. This can be further expanded, and you can write it in this form I k z I L z plus I k x I L x plus I k y I L y. Okay, so this is the effective. This is the effective Hamiltonian that we obtain after this T1 time period. And we see that the chemical shifts are eliminated. Okay, now that there will be evolution of this magnetization components under the influence of the only the in this T period, right? So now what we can write is that, so this IKX will also evolve in the T period, AGT period, and what we have is this one. Okay, so I'll just derive this part. This is IKX 1 plus cos 2 pi J T by 2 plus ILX 1 minus cos 2 pi JT by 2. And then you have these terms 2 IKY ILZ minus 2 IKY or ILY. So for L spin, it will be ILY IKZ sine 2 pi. This is multiplied by sine 2 pi JT by 2. Okay. So you see here both this is the diagonal, this is the diagonal peak term. So this term is responsible for the diagonal peak and this term is responsible for the cross peak. So both this diagonal peak and cross peak have the same phases. Okay, we'll have the same phases and similarly you can write this for ILX, right? You can also write this for ILX and uh, and that is what I had written over there. That for this ILX, this will be what? It will be minus I cos 2 pi. So here this was minus for this I case. This will become minus 1 minus cos 2 pi JT by 2. ILY. So this will be ILY IKZ plus this will be minus. So when you add these two expressions, then what you get is that in this period there is no the X magnetization remains constant. Okay, IKX plus ILX. This will become equal to because all these terms will get cancelled. These ones will get cancelled with this term, and when you when you open these brackets and solve this, these terms will also get cancelled. Okay. Now coming to heteronuclear cozy experiment. So heteronuclear cozy experiment. There is yeah, as this term suggests, heteronuclear cozy means what? There will be two nucleus means I and S. So I here means that is this proton, and S can be any atom. It can be carbon, nitrogen. And the so here in heteronuclear cozy experiment, the RF pulses can be specifically selected to excite either species. Either the RF pulse will excite this. So since there are two spins, there are two nuclei H, and there is a proton, and there is another nuclei which can be anything. It can be carbon, nitrogen. So we can selectively excite either spin by applying the particular frequency. Okay, so here you see that there are two channels in a heteronuclear cozy experiment. Two channels are present. One is for the proton, one is the proton channel, and another is the X channel. And why are these two channels present? So these two channels are present for selectively exciting the space. Now, in the heteronuclear cozy experiment, only cross peaks are recorded in a heteronuclear spectra. Okay, we will not get any diagonal peak. Okay. The coupling information is present along both the axes. The 2 XY HZ is the product operator term. This one, this 2 XY HZ is the product operator term that results in the antiphase nature of the fine structure in the cross peak. Okay, because this 2 XY HZ, what does it mean? That it is the Y spin is anti phase with respect to the X spin is antiphase with respect to Z. Okay. So here you see in this is a heteronuclear cozy spectra that you obtain here. First you apply this 90-degree pulse, and then this is this is transfer followed by a T1 time period. And then following this 90-degree pulse, there is this 2XY is obtained. And so here, what you get, you only get the cross peaks. There are no diagonal peaks obtained in a heteronuclear cozy experiment. Okay. Is it clear? So, so try to answer this question in a heteronuclear cozy experiment with the pulse sequence 90x H1. So 90x H1 means we are selectively exciting the proton nuclei by application of 90-degree pulse in the x direction. This is followed by T1 period. Then following this, there is 90-degree x pulse, which is selectively, which is exciting this 90-degree x pulse. So as I had shown here, this 90-degree x pulse, this 90-degree pulse is exciting both this proton and this X nuclei. Okay. So that is what he's shown over here, this 90-degree X, which is H1C30, means it is exciting both this proton and the C30 nuclei. Then there is T2 period and acquisition. So which of the following is true? So for a heteronuclear cozy experiment, the CH crosspeak has no fine structure. The CH crosspeak has fine structure along F2 only. The CH crosspeak has fine structure along F1 only. The CH crosspeaks have fine structure along both F1 and F2. So you see over here, there is, so if you see the cross peaks over here, so here this cross peak is blown up over here and magnified, and you see that, and this cross peak has fine structure in both this F1 direction dimension also and in the F2 dimension also. So a heteronuclear cozy experiment. So since there is no decoupling done over here, so the fine structure will be obtained in both the F1 and F2 dimension. Okay. So now answer the question. So the CH cross peak will have fine structure along both F1 and F2 dimension, right? Because we are not doing any decoupling. So that is why they are both. That is why we will obtain cross peak in both the F1 and F2 dimension. So if we had to remove these fine structures, then what we had to do, then we had to apply this broadband decoupling. So if we apply this broadband decoupling, then only the fine structures that we are seeing in the cross peaks along both the F1 and F2 dimension, those will get removed. So so the fine structures in the cross peaks will be removed only by applying broadband decoupling or BB decoupling. The antiphase magnetization is refocused into an in-phase magnetization by applying an inept sequence. Thereafter, a decoupling is applied. So here you see that first there is the first, this 90-degree pulse is applied. This is for the H nuclei, and this is for the X nuclei. So first, we start with this 90-degree X pulse, which is selectively exciting the X nuclei. Then a time period T1 is applied, and then after this T1 period, there is refocusing. The antiphase magnetization, this antiphase magnetization that we are seeing here, this 2XYZ, this antiphase magnetization, it gets refocused by applying this inept pulse sequence, 90-degree 1 by 4J, 180, and then again 1 by 4J. Then this causes the refocusing of the pulse sequence, and then after refocusing the in phase, we get an in phase magnetization, and then this in phase magnetization is decoupled so that the cross peaks in the F1 and F2 dimension gets removed. Okay. So what is happening over here? So in this T1 period, the proton the proton, in this T1 period, this proton magnetization is evolving with its characteristic frequency. Okay, now this pair of 90-degree X pulses, you see here this pair of 90-degree pulses you applied simultaneously. What will this do? This will transfer the magnetization. This will transfer the magnetization, and the transfer coherence from the proton to the X nucleus, and the X nucleus is ultimately detected during the T2 period. So you see here the X nucleus is detected in the T2 period. That is why in the F2 axis you have this X nuclei, or the frequency of the X nucleus present in the F2 axis, because you are detecting the X nuclei in the T2 period, in this T2 dimension, while you are detecting the H1 in the F1 dimension. That is why you have H1 in the F1 axis. Okay, F1 axis. So why do have you have coupling? So there is a coupling evolution here, and the proton X this coupling evolution happens with the proton. So because X is coupled, so here X is coupled to proton, right? So therefore the structure will be very similar to what we get in a cozy cross peak, and so the fine structures will be obtained in both this F1 and F2 dimension. Okay, now we will come to heteronuclear single quantum coherence experiment. So in a heteronuclear say HSQC experiment, what we want to do is that since we are obtaining these the fine structures in the cross peaks. So that is not giving us any information. We want to eliminate those fine structures in the cross peak. So then this HSQC, the transfer of magnetization takes place from proton to X nucleus. So X nucleus is a can be any can be carbon or nitrogen, which has a lower sensitivity. It has the sensitivity of these nuclei is less because they have a lower gyromagnetic ratio, and also the abundance is less. So we want to transfer the magnetization from the proton to X to the X nuclei. So that is what we had seen in the polarization experiment. So that is what is done in here also. So the magnetization from a more sensitive nuclei is transferred to a less sensitive nucleus, and this is done by introducing an inept sequence. So here you see, if you see this pulse sequence, here this is a 90-degree pulse, then followed by 180-degree pulse, and then again there is a 90-degree pulse. So this is an inept sequence. So in this inept sequence, first we excite this proton by this 90-degree expulse. Then following this T tau period, this what the 180-degree expulse is applied to both this proton and X nuclei. Right. And then again, following this tau period, the 90-degree pulse is applied to both this proton and X nuclei. So in this period, in this throughout this period, okay, before this time point two, this inept sequence, what it does, it transfers the magnetization from the H nuclei to the X nuclei, from the proton to the nuclei. So the HS in the HSQC, the main change that we are doing is we are introducing this inept pulse sequence, and this inept pulse sequence is helping us Inept pulse sequence is helping us transfer the magnetization from the proton to the nuclei, from the X nuclei, which is less sensitive, NMR sensitive. Okay. So then at point two, at this time point two, there is the antiphase magnetization. Okay. So once this 90-degree X pulse is applied, it will move to the transverse plane. Then after revolution, it will have antiphase magnetization. This antiphase magnetization is present. So we want to remove this antiphase magnetization, and so another 180-degree pulse is applied. So once this 180-degree pulse is applied, this HX coupling that will be present, that will get removed. Okay. So between the time points 2 and 3, no chemical shift evolution is happening for proton. So since this was, so you see over here that this 180-degree pulse is applied to the proton. So once this 180-degree pulse will be applied to the proton, this will get decoupled. This will get decoupled from the X nuclei. This will get decoupled from the X nuclei. So between the time period 2 and 3, there are a couple of things that will happen. First, this HX coupling will be removed. HX coupling will be removed, and there is no chemical shift happening during this period. The chemical shift will get refocused after the application of this 180-degree pulse, and so this 180-degree pulse, it refocuses the chemical shift, and as a result there will be no chemical shift evolution. And also this 180-degree pulse, because it is selectively applied to the proton, it will cause the proton to get decoupled from the X nuclei. Okay. So that is the purpose of HSQC. We want the proton to get decoupled from the X nuclei. We only want the cross peaks, or we only want the we do not want those fine structures that we were getting in the heteronuclear Posey experiment. Now here these terms you see, so this is the time point at time point one. At time point one, the product operator is HZ, right? Because we have we have only the proton, which is in the oriented in the Z direction. So this is HZ. Then following this T2, at time point T2, there is antiphase magnetization. So this one, this 2HZXY. This term is antiphase magnetization. This is present, and then this will evolve for this T1 by 2 period. And in this T1 by 2 period, because till this point the chemical shift evolution taking place, and this will introduce the term F of T1 in the rho 3 product operator. Then this 90. Then yeah, so the chemical evolution was taking place for this T1 by 2 period. So there we have this F of T1 introduced in this term, and then at when this 90-degree pulse is again applied, so yeah, this following this 90-degree. So you see the narrow bar. This narrow bar is the 90-degree pulses, and these are the 180-degree pulses, broadband. These are broad piece. The magnetization of H is detected by decoupling the X nuclei. So this GRP, this is what at the T2 period, this proton we are detecting in the T2, in the F2 dimension we are detecting, and before detection this coupling to the X nuclei is removed by applying this sequence. Okay, so this rho 5, ultimately the rho 5, this period we are giving, it represents the in-phase proton magnetization. There will be no fine structures in the cross peaks. There will be no fine structures in the cross peak, and so during the T1 period the HX coupling is removed by in the T1 period, the HX pulse recoupling is removed by applying 180-degree pulse to the proton. So this is the 180-degree pulse that is applied to the proton. So once this 180-degree pulse is applied to the proton, the coupling between the HX will get removed. And during the T2 period, the X nucleus is decoupled to the proton nucleus. Right. This will get decoupled to the X nucleus will get decoupled. So we are independently detecting the H and X nuclei. So in the T2 dimension, we will have the F2 dimension, we will have the peak have the HP peak for the proton, and in the T1 dimension, we are detecting the X nuclei. So there will be no fine structures present in the cross peak of F1 and F2 axis. Okay, so this is the HSQC spectra for a protein. So you see that on the that for a protein you have this amide protons, right? CONH, the peptide bond will have these amide protons, and all these amide protons will give you each amide protons in an amino acid will give you peaks, will give you individual peaks in an HSQC spectra. Only the proline does not have a NH amide proton. That is why proline does not give you amide proton, while all other amino acids will give you a peak in the HSQC spectra. So that is why HSQC gives us the fingerprint of a protein. Okay, so all the amino acids will give in the protein will give you will give you a particular peak in this spectra, and also you see that in this HSQC spectra there is significant enhancement in the signal to noise ratio that is takes place by this indirect detection scheme. Indirect detection scheme means we are detecting the proton in the F2 dimension and the X nuclei in the F1 dimension. So that is why there is significant enhancement. So now answer this question in an HSQC experiment, which of the following statements are true? There is no fine structure in the cross peaks. Yes, that is true. We saw just now that since there is the first a decoupling is caused by applying 180-degree X pulse selectively to the proton. That is why this at this point the proton gets decoupled to X, and then during the detection period, during the T2 period, we are once again applying the decoupling, BB decoupling, and because of this, X nuclei gets decoupled, and so there are no fine structures in the crosspeak. The signal to noise is much superior compared to direct X detection experiment. This is also true. The signal to noise ratio or the signal to noise is improved in an HSQC experiment is inferior. This is false. Cross peaks have fine structures along the F1 axis. This is also false. So there is no fine structures in the F1 and F2 axis. Okay, so option A and B is correct. Now answer this question. In a proton C13 HSQC experiment, maximum transfer from proton to C13 will occur for a value of. So what you were seeing that the transfer of magnetization from proton to an X nuclei, when X nuclei were was taking place by introduction of the inep sequence. And in an inep sequence, what do you have? You in an inep sequence you have this 90-degree tau period, 90-degree tau period, then again 180-degree. So this tau is equal to what? This tau becomes, and again there is this tau period. So all this tau becomes equal to, this tau is equal to 1 by 4j, right? In an inep sequence. In an inep sequence, this is what I was showing here. I'll show you. So this entire sequence, this 90, 180, 90, and this 180, 90. This is the inep sequence. This in this inep sequence, this tau is equal to 1 by 4j. Okay, I'd also taught you this in when we were discussing inept in detail. So the answer for this question is 1 by 4 C J coupling constant between the proton and the carbon nuclei. So a typical inept sequence is applied for the transfer of magnetization. So we are transferring the magnetization from the proton to nuclei, and the transfer takes place when we apply this inept sequence per sequence. So that is why the answer will be 1 by 4 coupling constant between the proton and the carbon. Now, in a C13 experiment, the proton appears along F2 axis and C13 along the F1 axis. So what we were doing in the HSQC experiment, we were detecting in the T2 period. In the T2 period, what we were detecting? In the T2 period, we were detecting the proton, right? And in the T1 period, we had this X nuclei, right? We had this X nuclei. So what we will get? So in the T2 dimension, we will have the proton, right? And the C13 will appear along the F1. This is the correct option. The proton, yeah, because the proton, so you can see over here also, this figure. So here you see this figure. In this figure, this proton, here you are detecting in this T2 period. You are decoupling the X nuclei by applying this by applying this decoupling. And so you're detecting this proton in the T2 period and the X nuclei detecting in the F1 period. Okay. Is decoupled from the X nuclei and appears in the F1 axis, while the frequency of X nuclei appears on the F1 axis. Okay. So which of the following is correct? The NOSI is useful for peptides with 1 kilodalton molecular weight. Toxi aids in spin system identification and gives correlation with neighboring residues in peptides. HSQC gives the fingerprint of peptides or proteins. So this option is correct. Just now we saw the HSQC spectra of a protein. So all the different amino acids will give a peak in the HSQC spectra corresponding to the amide proton. Okay. The toxi aids in spin system identification and gives correlation with the neighboring residues and peptides. So this is not true. Neighboring, not only neighboring residues, but also the other residues to which it is indirectly coupled. And NOSI is useful for peptides with 1 kilodalton molecular weight. Not only 1 kilodalton, but also we can use this for higher molecular weight peptides also. Okay, for proteins also it can be used. So the option C is correct. The NOSI is used in NMR to identify through space interaction between protein. Because in NOSI, what we are doing, we have dipolar-dipolar coupling. The interaction is taking place through dipolar-dipolar coupling or dipolar coupling, and that is why we see that all the protons that are within 5 angstrom distance, all those protons, we will get a peak for those protons. And they can also be applied to larger proteins or peptides. Okay. And in toxi, not only do we get the correlation with neighboring residues, but also the other residues in the peptide. Okay. It works to connect protons with the same residue, but to coordinate residues across peptide bonds. So yeah. Okay. It gives correlation with the neighboring residues in the peptide. So this is false. This is false. Why? Because here you will have this NH and then you will have this CO group. So once you have this CO group, then the toxin will not give you any peak for the neighboring residue in the peptide. It can only give you the peaks for those protons which are in the for the same amino acid. For a particular amino acid, if you will have alpha proton, beta proton, gamma proton. So all the protons that are in a particular amino acid. Only for those protons we will get a peak, but we will not get any peak for the adjacent residue in a peptide because there is this carbonyl group also, this NHCO bond, this peptide bond will not it the coupling or this magnetization transfer does not take place if there is a CO. That was what I was discussing when by giving an example of ketone group. Okay. And now in try to solve this question, this is in a 3D NMR experiments, you have three time points. One is 256, data T2 is what 512, and T3 is how much? It is 1024. And the acquisition time is 0.2 second, relaxation delay is 1 second. The total acquisition time with 4 scans. So you are doing 4 scans for each FID. So how will you calculate this? So total time, if you want to calculate, just multiply 4 with 256 and 512. Okay, and each scan is taking how much time? It is taking 1.2 seconds, right? So there is an acquisition time of 0.2 second and relaxation delay of 1 second. So total is 1.2 seconds. So if you calculate this, you will get around, this will give you around 7.3 days. Okay, so the correct answer is 7.3 days. So that was all for today. I hope the session proved to be useful. Okay, so we will take up more questions and also next, so this was the last problem solving session for this week. And in the next session, we have another 1 hour problem solving session. Where I will summarize the important concepts of this course. And if you have any doubts, you can take up those questions as well. So, so that was all. And thank you for your attention. We'll meet you in the next session.